Welcome everybody to Algebra 2, Section 7.1, Graphing Exponential Functions. So, an exponential parent function, just like all of our other parent functions, is the most basic version of an exponential function. And this would be f of x equals b to the power of x, where b is some number, some real number to clarify, so not imaginary numbers. And notice the x is in the exponent, hence exponential. And if b is greater than 1, this graph is what we call an exponential growth graph. And that is because it'll be increasing. And when you think of increasing exponentially, it just means increasing incredibly fast and literally by using exponents. And if b is less than 1, such as like 1/2 or 2/3 or 3/4, then it's what we call an exponential decay. So once again, we either have exponential growth or exponential decay, and it all depends on whether or not b is greater than 1 or less than 1. And exponential decay then would be where it's decreasing rapidly. And that's what you would see with like half-lives of carbon half-lives, for example, of different materials. Now an asymptote, this is something that's new to us here. So an asymptote is a line which the graph never, let me clarify that, which the graph approaches but never reaches. So it's this line that it gets closer and closer and closer to, and just infinitely closer to, but never actually touches it, as I just sharpen up my writing here on some of these words. And we'll see that play out here with our asymptotes today. That it gets super close to these lines and to these spots in the graph, but never actually gets there. I'm going to fix the A in my approaches and then call it good on this. Or at least good enough. And so now we're actually going to start graphing. So we're going to classify these as exponential growth or decay based upon the value of b. And then we're going to graph, identify the key characteristics over here on the side. And we're going to graph by making a table. So because b is 2, 2 is greater than 1, so this is an exponential growth. So this is growth. And we're going to make a table. And a good bet for values of a table typically are going to be the x values of -2, -1, 0, 1, and 2. And these are nice numbers to pick because, one, they're integers, so they're non-decimals, non-fractions, which is handy. And two, they give you an idea of what's going on both positive and negative sides of the graph, as well as the middle of the graph. And so these are just the numbers I pick. You could technically pick any numbers, but I would just encourage you and have you pick these as well. And what you do is you just plug these in. So 2 to the power of -2, and say, okay, what would that be? Well, the actual math behind this would be that would be 2 to the power of -2 is really 1 over 2 squared, because the negative exponent just means you move it. And so it's 1 over 4. And that's 0.25. Now I could write 1 over 4, and I typically prefer fractions, but one of the rare occasions where I actually prefer decimals is when graphing, because I can actually see 0.25 on a graph a little bit better than I can see 1/4 on a graph typically. And so we continue doing this with -1, 0, 1, and 2 for all these different x values. And so 2 to the power of -1 would be 1 over 2, or 0.5. 2 to the power of 0, anything power of 0 is 1. 2 to the power of 1 is 2, and 2 to the power of 2 is 4. And so now I go ahead and graph these. So -2, 0.25, -1, 0.5, just barely higher. You can not even really tell. 0, comma 1, once again barely higher, 1, comma 2, and 2, comma 4. So we start getting quite high. And if I kept going, for example, I would have 3, comma 9, or let me try that again, 8, because it'd be 2 to the third, and so that would be all the way up here. And if I did 4, that'd be 2 to the fourth, which is 16. And so you notice that would be increasing incredibly rapidly to where the y values go from 1, 2, 4, 8, 16, because these are all powers of 2, increasing, as we say, exponentially. And so now as we trace this graph, actually what happens here is they increase super fast, but as they go to the left, they never actually reach 0. So notice my blue line, I made sure it didn't actually ever touch 0. And I'm trying to zoom in here, but my iPad just is not wanting to cooperate with me. There we are. And so I made sure it never actually touched 0. It got really close, but it never actually touches it. And we can actually see this on our graphing calculator. So if we go to a graphing calculator of some sort, so I'll go to Calc84, for example. You can go to Desmos as a graphing calculator. They have a great one there. You can also go to our just TI-84s that we use in class. Y equals, I type in f of x, or y equals 2x, 2 to the power of x. Remember, our exponent button is directly above the division symbol, where it has a little caret button. And then I go to graph, and I can see that, yes, it increases incredibly rapidly as I zoom out. I should go back to zoom standard and then use this zoom out button. That works a little bit better than actually pinching and zooming on this, unfortunately. The pinch and zoom doesn't work very well. And we can see it goes up super fast, but to the left, it just continues to hug y equals 0, the x-axis. And if I continue to zoom in, I just do this pinching again here, though, just to increase rapidly, or zoom in rapidly. We can notice that it's still, as we just keep zooming in and zooming in and zooming in and getting incredibly close to this y-axis, that it's never actually going on the other side of the y-axis. And Desmos actually does a slightly better job of showing this to where it shows it slightly farther away from y equals 0 than this one does. It shows it essentially on top of it, but Desmos would actually show a little bit of a gap there, just as microscopic as that gap would be. It shows a slight gap, which does exist. And so it just never actually touches it, which is that asymptote like we were talking about. Now, something I want to mention as well, that if you wanted to find these x and y values at table in order to graph, something you can do is you can type those values in a calculator, like 2 to the power of blank, 2 to the power of blank, 2 to the power of blank. But you can also type in your function of y equals like we just did, and then instead of hitting graph, go to second and hit graph, and it gets to the table button. And now if we use the arrow up and arrow down, as you can see, I'm going to hit clear. But as I do arrow up and arrow down, as you see me clicking here, you can see these values of -2. This, I guess, organized it interestingly. That's odd. But -2 with the y value of 0.25, 0.5, 1, and then 1 again with 0, 1, just restarting it, 2 and 4, and then 8 and 16 like we talked about. And so we see these x and y values show up here, and that's something that we can utilize to make our life a little bit faster if we want. Now let's talk about some of these key characteristics. So for all exponential functions that we'll be doing in Algebra 2 and just any standard exponential function in general, the domain is going to be all real numbers, which is a double line R. Another way to word that was the negative infinity, comma infinity, with parentheses on each side of it. Because infinity and negative infinity always get parentheses, no brackets for those. And that just means every x value is part of this. As you can go negative forever, you can go positive forever. The range, though, it doesn't go down forever and it goes up forever. And so one way to write the range would be y is greater than 0, specifically not equal to it, because it never reaches or touches 0, because that's where that asymptote is. And the other way to word it would be 0, comma infinity, with both being parentheses. 0 being a parenthesis because once again it doesn't actually reach 0, and infinity being a parenthesis because it's a concept, you can't reach it, and it's always a parenthesis. And the range on these will never be negative infinity, positive infinity, or the all real numbers. It'll always be y is greater or less than a number, depending on where the asymptote is. or something comma infinity or negative infinity comma something, once again, depending on where the asymptote is. So the asymptote will always be involved in your range, these exponential graphs. The end behavior here, so what's happening as x approaches positive infinity, they have the positive and negative infinity reversed in this notes here, so we have to take note of that. I typically do negative infinity first, positive infinity second, so just a heads up. As x approaches the far right side, what's happening? Well, the y's are approaching positive infinity. But as x is going forever left or negative, the y's are approaching 0. Now, we said it doesn't actually get to 0. Well, it doesn't actually have to get there. It doesn't get to infinity either, because you can't get there. But it's saying it's approaching, or that's what it's heading toward. And that gets back to this idea of an asymptote. It's a line that the graph approaches, but never reaches. So the left end of the graph is getting closer to 0 as x gets closer to negative infinity, even though it never actually gets to 0 or negative infinity. The y-intercept is where it crosses the y-axis. You can always find this by plugging x equals 0 in. And on the graph, it's visually where you see it cross the y-axis, and that's 0, 1. And on a lot of these exponential graphs, you'll see no x-intercept because it didn't cross the x-axis, since that's where the asymptote was. Which brings us to asymptote. This is going to be y equals a number, because it's a horizontal line, and horizontal lines are always y equals a number. So this will be y equals 0, because it never actually touches or reaches 0. And so you might want to make a note here that asymptotes will always be y equals a number for exponential functions. These are what we call a horizontal asymptote. There are other types of asymptotes, but we will specifically be talking about horizontal asymptotes with exponential functions only, and they will always be then y equals a number because it's a horizontal asymptote. So moving on to number 2 here, I can already pencil in my domain. My domain is going to be the all real numbers, with the double-lined r, or the negative infinity comma infinity, because it will be that on all of these exponential function problems. And I can go ahead and make my table here, x, y, and the x values of -2, -1, 0, 1, and 2, just the standard 5 I'll be picking. And I can identify this as growth, not exponential decay, because b is greater than 1, 3 is greater than 1. And so now if I want to figure out, okay, what would these y values be, I can actually plug in, 3 to the power -2, 3 to the power -1, 3 to the power 0, or I can, once again, use my graphing calculator if I want, or any calculator if I want as well. And I end up getting the decimals 0.1 repeating. I do want to emphasize that is repeating there. 0.3 repeating, 1, 3, and 9. And so I'm going to go ahead and plot these. So -2, 0.1 repeating. So basically just incredibly close to the y-axis or x-axis. -1, 0.3 repeating. So similar scenario there. And then 0, 1, 1, 3, and 1, 2. And 2, 9. So way up there, it shot up very fast. And you're going to see these increasing and decreasing very quickly, like we're talking about. And as you can tell, my line kind of bumped up a little bit there. And is that how the graph actually looks? No, but I drew mine imperfectly because I'm an imperfect human. And that's okay. So the range here, well, what's the lowest it goes? Well, it never actually gets to 0, but it gets close. And so the range is y is greater than 0, or you could say 0, infinity. And then the end behavior is going to be very similar to last time. As x approaches positive infinity, the y's are approaching positive infinity. And as x is approaching negative infinity, the y's are approaching 0. The y-intercept is actually, again, 0, 1. That won't always be the case, but it was the case both times on 1 and 2. Once again, will not always be the case. It'll actually be the case on 1 through 5. It'll typically be the case, I should say. Just like the asymptote is, again, y equals 0, which will also not always be the case, but is often the case. And the reason why the y-intercept is often the case as a 0, 1 is because most often you'll just have something to a power, And when you have anything to the power of 0, you get 1. And so when you're raising something to the power of 0, you're getting 1 out, like we mentioned. And so until there's transformations, which we won't see until after we're done with examples 1 through 5, then you're just going to have it be 0, 1 every time. Moving on problem 3. So we're going to go ahead and classify this one as not growth, but rather exponential decay. And the reason we're classifying this as exponential decay is because this is 1/2 being raised to a power, and because b is less than 1, 1/2 is less than 1, it'll be continually getting smaller and smaller and smaller, and we'll see this pan out in the graph as such. And so let's go ahead and make our table. I'll use the same x and y values, or x values I should say, and as I plug these in, I end up getting the y values at 4, 2, 1 again, because anything with the power of 0 is 1, 0.5, and 0.25. So this is the exact opposite of what we saw with 2 to a power, because it's just the exact reciprocal of 2. So as we go and plot these, and if we kept going to the right, it'll be approaching 0 but never getting there. And to the left, it would eventually go to 8 and 16 and 32 and so on and so forth. Domain we could have penciled in early, saying that's all real numbers, or (-infinity, infinity, as they'll be on all exponential functions, even when we do have transformations. The range is again y is greater than 0, which once again is always linked to our asymptote, which once again will not change until our transformations make them change, which is 0, not negative, but 0, infinity, with parentheses on each. End behavior here, as x approaches positive infinity, y is approaching 0, and as x is approaching negative infinity, y is approaching positive infinity this time. So a change in our end behavior because we're decaying or getting smaller rapidly. The y-intercept is 0, 1 again, which it'll be the case until we have transformations that affect it. And the asymptote is y equals 0 again, which once again will be the case until we have something that affects it. So you'll notice that domain, range, y-intercept, and asymptote are saying the exact same every time, and end behavior might flip-flop or might stay the same depending on whether it's growth or decay. And these are going to be that way on 1 through 5 because there's no transformations, but transformations will affect these. So on number 4, we'll make our table. Use the same values. And if we plug in 2/3 to the power of -2, -1, and so on and so forth, we get the following y values: 2.25, 1.5, 1, 0.6 repeating, or 0.6 repeating, and 0.4 repeating, or 0.4 repeating. And I'm going to go ahead and graph this. And really, in order to see more of this graph, it might not be a bad idea to insert a couple extra points here. I ran out of room up here, though, so I'm just going to put it down at the bottom. So it would be, for example, like -3, comma. Oh, that's a great question, actually. I should have been more prepared to have that. Well, let's go to the graphing calculator and find out, actually. So let's do 2/3 to the power of x. Graph. Oh, I didn't mean to go to graph. I meant to go to table. There we go. And -3, 3.375. That's why I wasn't getting it. -4, almost 5, and -5, 7.5. So I'm just going to plot those. And I just kind of rounded on some of those last ones there as I was just trying to remember them from a different screen. And then you can actually start seeing a little bit of that exponential growth. The domain would again be all real numbers, aka negative infinity comma infinity. The range is again y is greater than 0, aka negative, 0 comma infinity, not negative. And the end behavior would be the same thing as on 3, since this one is, I forgot to label it as such, but it is decay, because it is, b is less than 1. But the end behavior here would be as x approaches positive infinity, y approaches 0, and as x approaches negative infinity, y approaches infinity. And then the y-intercept is again 0, 1, and the asymptote is at y equals 0. And on number 5, this one is again growth, even though we see a fraction, 5 halves is bigger than 1. It's 2.5 after all. So as I go ahead and make this xy table, I'll just go and use the same values as before. 0.16, 0.4, 1, 2.5, and 6.25. And we can already see that exponential growth starting to occur as you plot these. The domain would again be negative infinity comma positive infinity, or the double-lined R. The range would again be y is greater than 0, aka 0 comma infinity. The end behavior would be as x approaches positive infinity, y approaches positive infinity, and as x approaches negative infinity, forever left, y approaches 0. And the y-intercept would be 0, 1 again. And the asymptote would be y equals 0 again. Now let's get into some transformations. So for transformations, we're going to have a lot of similarities to what we saw in absolute value or quadratics when we saw transformations, to where we have an A, an H, and a K. And A affects reflections as well as vertical stretch and vertical compression. And H will affect horizontal movement, the shifting left and right, and K will affect the vertical movement, aka the up and down. And we're really going to see the exact same nuances as before with each of those. So H is our horizontal shift, as I just mentioned. And that's one that's with Rx. And because it's x minus h, that one's a liar. So positive actually shifts it left, and negative shifts it right. And so remember that this one is, in fact, a liar. I keep mentioning that. And then K is the vertical movement. And positive shifts this one up, and negative shifts it down, which is a lot more straightforward. Positive is up and negative is down. And if A is negative, then the function is reflected, which is the same as once again before. So nothing new here so far, and it's reflected across the x-axis specifically, so, or a vertical reflection is the way to think about it. And if the absolute value of A is greater than 1, aka numbers like 1.5 or 12 or 28 or you name it, then it's a vertical stretch. And if the absolute value of A is between 0 and 1, such as like a half or 2/3 or 3/4, then it's a vertical compression. And we don't worry about horizontal stretches or compressions because it's just the opposite of a vertical stretch or compression. When something is stretched vertically, it is compressed horizontally. And when something is compressed vertically, it is stretched horizontally. So on 1 through 4 here, we're going to identify the parent function in step A. And in step B, we're going to describe the transformations that have then since occurred. So the parent function is the b to the x part. So the parent function is going to be f of x equals 3 to the power of x. So that means the transformation is everything else, aka the plus 5. So what did the plus 5 do? Well, that's our plus k, because it occurs outside of away from our x, and it's adding. So that means it's going to be a shifting up 5. Now remember, you could use the word shift, translate, or slide. Once again, shift, translate, or slide. But you do need to include that it's going up, and that it's going up 5 specifically. On number 2 here, part A is, remember, the b to the x, so that's 1/4 to the power of x. And that doesn't need to be in parentheses, emphasizing that it's not just 1 being raised to the power of x, but it's 1/4 being raised to the power of x. And then part B is the transformation. So this 2 is doing something, and this -1 is doing another thing. So the 2 is multiplying as our a out in the front. It's positive, so it's not reflecting it. And because it's greater than 1, it's going to make it bigger, aka stretching it. So it's going to vertically stretch. If you just write stretch, that's fine with me, since we're only dealing with vertical stretching. By 2. And then, what else is it doing? Well, this -1 tells us a horizontal change. And because whenever it's with the x is horizontal, and it's always a liar. So even though it's subtracting, it's actually going to move it right by 1. And so it's going to be a shift right 1. And once again, you can use the word shift, translate, or slide. On number 3, our original function is f of x equals 4/3 to the power of x, which means that there are 3 transformations: the negative, the +2, and the +7. So the negative means that it reflects across the x-axis, which you can just say reflects, but I will mention that it reflects across the x-axis specifically, or you can also say reflects vertically. It also, this +2, that's a liar for horizontal movement. So it's going to shift, translate, or slide left 2. And then this is telling us it's going to shift, translate, or slide up 7, which I can just include and up 7. Or I can include as the third line and say shift up 7 if I want to. But I'm lazy and I like to write less. So then on number 4, part A is this 5 to the power of x specifically. Is the original function before the transformation. And then the part B is everything else. So let's start with the 1/2. So that is not positive, so it's not reflecting. And it's less than 1, so it's going to make it smaller, aka a compression. So it's going to vertically compress by 1/2. And if you just say compress by 1/2, I'm fine with that. That's one part. And this -4 tells us that it shifts right 4, because it's a liar, and it's horizontal. And this -2 tells us it shifts down 2, which I can just include in the same shifting mention, or line. And now we're going to use these transformations as we graph these next and last 5 graphs. So we're going to graph the function, identify its key characteristics. So f of x equals 2 to the power of x plus 5. And the beauty is we can just do this the exact same way we did before, where we can plug this into our graphing calculator and hit the table button, or just plug them individually. 2 to the power of 1 plus 5, aka 2 to the power of 6, 2 to the power of 0 plus 5, okay, 2 to the power of 5, things like that. And what I typically do for these is I take this plus 5, and I know since that's going to make it so I'm shifting at left 5, horizontal movement, and it's a liar, is I'm going to adjust where my x and y, where my x's are. So instead of picking -2, -1, 0, 1, 2, those numbers are going to be incredibly high here and go off my graph because of the fact that it's exponential growth. We have to be very careful about which points we pick. And so what I'm going to do is I'm going to adjust all my points by subtracting 5, or move each of my points 5 left. So rather than picking -2, I'm going to pick -7. Rather than picking -6 or -1, I'm going to pick -6. Rather than 0, I'm going to pick -5, and rather than 1, I'm going to pick -4, and rather than 2, I'm going to pick -3. And once again, the reason I do that is because I see horizontal movement. We're moving at left 5, so I'm going to adjust all my points left 5 to match. And we'll see it bear out on this graph that, that was actually a really good idea. And so now we plug these in, and as we plug those in, we'll get the y values out of 0.25, 0.5, 1, 2, and 4. And as I go and graph them here, noticing this graph is 10 left, 10 right, 10 up, and 10 down. I can notice this increasing quite rapidly. And you may or may not notice, but this is really the same graph as we had originally for number 1, which I guess decided to erase itself, but it'll pop up in a moment. Except for it's just moved 5 to the left because it's 2 to the power of x, and we did 2 to the power of x plus 5. And so we just had the same y values, and we even included the 3, 8, which would have been 5 less for the x value, so negative 2, 8. Is what happens here. And this does not affect the domain at all. The domain for these will still always be all real numbers, aka negative infinity, infinity. But we will see it affect range and behavior, y-intercepts and asymptotes at times. And so on this graph, we don't see it affecting the range. The range is still y is greater than 0, aka 0, infinity, because it didn't move this graph up or down or reflect at all. It only moved it left and right. And range is up and down, so it doesn't affect the up and down. And end behavior doesn't affect that either, because end behavior is saying what are the ups and downs doing. And so we're still going up forever as we go right forever, and we're still going to 0, approaching 0 as we go left forever. Now it does affect the y-intercept here. For the y-intercept, we can't just see it on the graph. We actually have to plug in x equals 0, and you can use this using your calculator as well, but essentially you just do 2 to the power of 0 plus 5, which is 2 to the power of 5, aka 32, so it's 0, 32, which, as I mentioned, if we did our original -2, -1, 0, 1, and 2, that would be so far off the graph, it's comical. If we had picked our original -2, -1, 0, 1, 2, we'd had numbers like -8, or +8, which actually does fit on the graph, 16, 32, 64, and 128, where only one of these numbers is actually graphable on our graph. And the asymptote stays the same here because, once again, nothing moved their graph up and down at all. So it's just y equals 0. Let's go on to our next example here, example 2. Here we have a vertical translation, shift, or slide. And it's being translated, shifted, or slid to down. And so because it's going down, not left or right, I'm not going to change my x and y values, or my x values that I pick. And so I'm just going to do -2, -1, 0, 1, and 2. Remember, the only reason I changed those in the last one is when there's horizontal movement or horizontal shift, slide, or translation. And so now as I plug each of these in, I end up getting the y values out of 7, 1, -1, -1.6 repeating, and -1.8 repeating. So we see that decaying starting from a bigger number going to smaller numbers, and it really slowing down there at -1, from -1.6 to -1.8 repeatings. So as I graph these, -2, 7, -1, 1, 0, -1, dipping below the x-axis for the first time. Then 1, -1.6 repeating, and 2, -1.8 repeating. And what's going to end up happening here is our asymptote must have moved. If we actually cross the x-axis, that must mean something allowed us to. And what the case is our asymptote is normally y equals 0. It's normally right here, y equals 0. What happened is because the whole graph moved down 2, the asymptote also moves down 2 and becomes -2. And so now -2 is this line that we never touch, but we get closer and closer to forever. And that's the only reason that our asymptote will change for exponential functions, is when we have vertical translation shifts or slides. And so that will affect our end behavior, it'll affect our range as well. Once again, is when we have these vertical translation shifts or slides, that'll affect our asymptote, which then affects range and behavior. And so our asymptote is really at y equals -2, as I mentioned, so I'm just going to go and fill that in. And I'm going to go and use that to graph here. And as I draw this, just make sure it never touches that, y equals -2. And my domain is unaffected, though. It's still the all real numbers, aka -infinity to +infinity as always, but my range, as I mentioned, is. So now it's no longer y is greater than 0, because y is greater than -2 is what it never reaches, what it gets close to. And so it's not 0, infinity, but rather -2, infinity. And so it always involves the asymptote. And then the end behavior here, as x goes forever right, it's not approaching 0, but it's approaching -2. And as x approaches -infinity or forever left, it is still approaching infinity. So it changes one of the end behaviors. And then the y-intercept here is wherever across the y-axis when x was 0, which we did already find, and that was 0, -1, which it affected that as well, because it moved it down 2. So it went from 0, +1 to 0, -1, subtracted 2 from it. Now we're going to move to number 7. On number 7, we have a few different transformations. We have a compression of 1/2, specifically a vertical compression, and then a vertical movement of 1 up. And so that shift translation slide of 1 up is going to move our asymptote up 1, by the way. So we can already know our horizontal asymptote will be at y equals +1, and that's because of this translation. I can already tell you where the asymptote will be for this one as well, for what it's worth, as well as the domain and range. Well, domain always, but range specifically. Without further ado, though, let's go and continue on number 7. So on number 7, there's no horizontal movement, though. No liar to worry about, so I'm just going to do the same -2, -1, 0, 1, and 2, which gives me 1.05 repeating, 1.16 repeating, 1.5, 2.5, and 5.5. And so as I do -2, 1.05, graph that, -1, 1.16 repeating, and you won't really see much of a difference between those at all because it's just so small of a difference. 0, 1.5, again, such a small difference. 1, 2.5, and 2, 5.5. You might be wondering, well, why is the difference so small? Well, the reason the difference is so small is because we compressed everything by 1/2, so we made it all shorter, vertically speaking. And remembering that our asymptote is at y equals 1, we draw it accordingly to where we never reach y equals 1. And so our domain is all real numbers again, aka -infinity, infinity, as it will always be. And our range is going to be, this time, y is greater than +1, aka tied to our asymptote again. And then 1, infinity, if you want to word it that way. The end behavior would be as x approaches positive infinity or forever right, y is going up forever, positive infinity. As x approaches negative infinity or forever left, y is going to positive 1. And the y-intercept here is 0, 1.5, which is a number we already found. On number 8 here, as I go and make my table, I'm noticing that there is horizontal movement, and it's saying -4. Knowing that number is a liar, that means I'm moving right 4. So I'm going to adjust all of my x values accordingly by moving them right 4, adding 4. So instead of -2 through +2, I will be doing +2 through +6. Now I can already know that the asymptote will be affected by this vertical translation, because we're vertically translated, shifted, or slid down 5, meaning my asymptote will be at y equals -5. Important for us to note. Now, one thing I should have mentioned earlier in the lesson is that we can do a dashed line at the asymptote. That's very common to do. And it's something I normally do, so I'm not sure why I wasn't doing it earlier. A dashed line at the asymptote just to showcase that's where our asymptote is. And so that's very commonly seen here, so I'm just going to go back in and fill this in on some of our graphs here, that you see a dashed line at where the asymptote is. And that's not because it actually shows up on the graph, but we just write them as a dashed line. So that way we see, oh, that's why it's not getting there, is because there's an asymptote. It's just understood that a dashed line typically means an asymptote. Now, dashed lines is also something we used previously when we did piecewise functions to denote the separation between one function and the next. But we won't be confusing the two here because these aren't piecewise functions. And these are also horizontal dashes versus vertical dashes. Anyway, moving on. As we plug each of these numbers in, we end up getting y values out, obviously. And so that'd be -4.5 repeating, -4.3 repeating, -4, -3.5, and -2.75. So all very close together still. So let's go and plot these. And so it's going to be hard to tell much of a difference on these initial points. And then on this last one, you'll see a little bit more. And then after a while, you would start to see more growth, by the way, if you ended up plotting more points, such as 7, 8, 9, and 10, in case you're curious. It would end up even going up to about there, approximately. But on the left, it never even never reaches, but it always approaches -5 for the y value. Domain would be the negative infinity, positive infinity, or the double line R, depending on your preference. And the range would be y is greater than -5 or -5, infinity, depending on your preference. Once again, tied to the asymptote. In behavior, as x goes to positive infinity, y goes to positive infinity, or forever up. And as x goes forever left, or negative infinity, y goes to 5, or -5 rather. And the x-intercept, where it crosses the x-axis, see the y-axis, for the y-intercept, I said x-intercept, we'd plug in the x value of 0. We end up getting the y value out of approximately -4.802. And that's one that we'd have to plug it in additionally, since we didn't plug in 0 initially. Let's move on to number 9, our last one of the day. So here we have this -2 out in front. That -2, the 2 will tell us to stretch vertically, but the negative will tell us to reflect this. So rather than looking something like this, or like a growth, or if it lets me undo it, perhaps, we'll see. It'll look something like this. It didn't let me undo it, but, you know, we'll work with it, I suppose. It'll look maybe like this, or this instead, because it's going to vertically reflect it. And this -2 is still going to tell us the same thing. That's going to move right 2, because it's a liar. So because it's moving at right 2, I'm going to go ahead and adjust all my x values accordingly, make it 0, 1, 2, 3, 4, rather than negative 2, 1, negative 2, negative 1, 0, 1, 2. My asymptote is going to be at y equals 0. Nothing changes there because there's no vertical transformation, translation, I should say. And so now as I plug in these x values, being careful to make sure I input that negative there. If I'm doing this by calculator, getting the x values of, or the y values of negative 1.25, sorry, 0.125, I put the decimal in the wrong spot. Negative 0.5, positive, sorry, negative 2, negative 8, and negative 32. Whew, rapid decrease. So I go and plot these. So 0 and just below the x-axis, 0 and also just below the x-axis, or 1 and just below the x-axis, 2 comma negative 2, 3 comma negative 8, and then 4 and way off the graph. So that decreased really, really quickly, and that's because we're doing 4 to a certain power, and then we stretched it even further. We doubled how fast it would decrease. So very fast decay. What would typically be very fast growth, because b is greater than 1, became a very fast decay because we reflected it. The domain is, again, all real numbers, aka negative infinity, comma infinity. The range is where we're going to see one of the places we're going to see a big change here, though. It's not going to be y is greater than a number, because it's no longer that number and up, the asymptote and up, is now below the asymptote. So it's y is less than the asymptote, or less than 0, which is going to be negative infinity, comma 0, because you start with the lower end and go to the upper end. And that's because of that vertical reflection, that negative at the beginning, which my circle and that negative 2 didn't erase well originally. Then as we go to the end behavior, as x goes forever left or to negative infinity, starts with positive infinity, as x goes forever right or to positive infinity, f of x or y goes to negative infinity. That's new. And as f of x goes to negative infinity or forever left, the y's or f of x is going to 0. And then the x-intercept we see, the y-intercept we see is 0, comma, negative 0.125. And that wraps up section 7.1 of Algebra 2.